Hello everyone, welcome to another Mammoth Site video. For our last video before the holidays, we wanted to do a fun little activity that kind of highlights one of my favorite things about studying geology and paleontology, and that is the truly vast amount of time we're working with. So behind me you'll kind of see, I've got this tape measure laid out to show just how vast geologic time is, with the start of the tape measure measuring the beginning of Earth's history, and then all the way down there, where Kelly's at, that marks today. So we've got about 200 feet of tape measure to work with. Now, on this tour of our geologic time, I'm going to highlight a couple different things that are kind of important, some fun little events that happen, and then we're going to talk at the end why it's important to understand geologic time as we go through. So, the first thing, we start at the very beginning, Earth forms, and then we're going to kind of start about 4.4, 4.5 billion years ago. Right about here on our timeline, just a few steps back, is when the moon formed. Now, there are two main ideas as to how the moon formed. We're not going to get into those today just because that's more of the realm of astrogeology and astronomy and things like that, but it's just something to kind of give you an idea of when things are happening along our timeline. Now, the next thing I want to show you guys is some of the earliest evidence of life. Now, the Earth's history starts about 4.6 billion years ago. The first life we find is about 3.7 billion years ago, which doesn't feel like that far along in our grand scheme, but when we look, we see that we're looking at a pretty big amount of time. In fact, we're looking at about all the way up in here, right at about 39 feet and 2 inches away. So right in here is the earliest evidence of life. Now, when people think of prehistoric life, they often think of fossils like dinosaur bones, and the earliest evidence of life on Earth is not dinosaur bones. What we're looking at here is essentially chemical markers in the rocks, chemicals that are really only found as the result of biological processes, so things like cellular respiration, things like that. So what we're looking at here, most of life at this time probably looked more or less like bacterial mats or algal mats. Kind of think what we call stromatolites today. Those are a pretty good indication of what those look like. And then the next piece of thing with that, what's really cool looking at all of these different microorganisms, is that they're actively changing the environment. In fact, the next event we're going to look at happened 2.4 billion years ago. Or on our timeline, give or take 95 feet, 8 inches, and that's what we call the Great Oxygenation. Alrighty, so the next event we want to take a look at is actually something that happens about 95 feet, 8 inches down our timeline, or somewhere around 2.4 to 2.1 billion years ago, which is an event that geologists and biologists call the Great Oxygenation Event. Now, event makes it seem like it's one thing, but in reality, as we're talking about, it's about several hundred million years of time kind of going through. But essentially, what it is it's when oxygen starts to become abundant in our atmosphere. Now, if we look at the world today, all the plant stuff around us that are producing oxygen, we can kind of take oxygen for granted. But what we can see is in the rock record, actually, we can see when oxygen started to become more abundant based off of a variety of different factors, one of which being a formation we call banded iron formation. Now, that's a specific type of rock that's essentially just rust in the rock record. Now, that rust is really important because rust itself is iron oxide. In order to have iron oxide form, you do need oxygen in the environment. So if there's a bunch of oxygen, you're going to start to see rust. So that's a really good indicator for us. And it's also really important because all of the big animals and stuff we see alive today require oxygen in order to survive. So in order for life on Earth to exist as it does today, we need to have this event happen. Alrighty, so after the Great Oxygenation, one of the big events, one of the ones especially for paleontologists that we get really excited about, is an event that happens or starts about, give or take, 545 million years ago. Now, 545 million years ago is a very long time from today. However, with this measuring tape analogy, it's about 3/4 of the way through Earth's history. Just to give you guys, again, some of that idea of scale, I've got Kelly all the way down there. And with that, with all of this stuff, the reason we get so excited about the Cambrian is because the Cambrian kind of is marked by the start with an event that's often referred to as the Cambrian explosion, but is more accurately called the Cambrian radiation. Basically, the rocks that we see from this time, we start to see a really huge increase in the diversity of different kinds of life there. Now, life existed in multicellular form before this time. We have a great example called the Ediacaran biota. But during the Cambrian, we start to see life as kind of we know it today. And although it's similar to the life we see today, it's important to remember that a lot of it would be would seem out of place today. One of my favorite animals from this time is called the Mammoths, so named because it's an anomaly. It's so weird compared to what we see today. It's basically, almost like a foot-long shrimp-looking animal with a big claw towards these big claws kind of towards the front of its mouth. You start to see things like trilobites. We start to see a lot of the groups that we see alive today. In fact, our earliest relatives, the earliest vertebrates, so the things that kind of encompass all the mammals, including the mammoths we have up here, exist at this time, and they're these little fish-like organisms. And so this is kind of when life starts to diversify and get really, 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 really weird. Moving from the Cambrian, after the Cambrian, we get into the Ordovician. Now, the Ordovician starts about 485 million years ago, basically. Once the Cambrian ends, that marks the beginning of the Ordovician. It starts right about here. Now, the Ordovician is personally one of my favorite times because that's when we first see examples of horseshoe crabs. So the same horseshoe crabs you might see alive today, that we can see animals that look almost identical to those that during the Ordovician, meaning we have an animal that's pretty much existed almost unchanged through almost 450 million years of history. After the Ordovician, we get into the Silurian, right here at about, give or take, 444 million years ago. During the Silurian, again, animals are changing. Some of the animals that are found in the Cambrian or in the Ordovician go extinct. New ones kind of evolve and adapt and take their places. One of the animals from this time period that's kind of one of the iconic animals is called a Eurypterid, more commonly referred to as a sea scorpion. We have examples of these from places like New York, these massive, invertebrate arthropod things that look like scorpions that were living in the oceans. Another animal group that comes about at this time, or at least the first examples we found so far are from this time, are sharks. Sharks appear somewhere around 420 million years ago during the Silurian. And then after the Silurian ends, we get into the Devonian. Now, the Devonian starts, give or take, 419 million years ago. And this one is another really important one, especially for vertebrate paleontologists, because this is where we find some of the first vertebrates, or the first tetrapods, coming onto land. Now, up to this time, a lot of the vertebrates were things like fish. This time we start to see some animals that you could kind of argue are not quite fish, but aren't quite amphibians. A great example of a Devonian animal that kind of fits that bill is Tiktaalik. It kind of looks like a fish. It kind of looks like an amphibian. It's kind of halfway in between, kind of shows the transition of animals going on to land. Now, at this time, before this time, most of the life was in the water. The reason animals started coming on land was probably because plants started to make their way onto land. Basically, conditions started to improve on land to the point where plants could grow, which become part of the food source. That would attract some animals. That would also attract even more animals to show up as well. Another thing to be aware of is during the Devonian, we've got these big fish swimming around, these bigger animals. Animals that could go on land, especially if they're a little bit smaller, might be able to survive and avoid being eaten by another larger animal that's living in the oceans at this time. And through time, as animals are able to survive longer and longer on land, we eventually get to the animals that we have today. Moving on from the Devonian, we get into a time period we call the Carboniferous at about 359 million years ago, or about 184 feet down our tape measure. The Carboniferous gets its name from carbon. The reason we think of the Carboniferous as, why it's named named after carbon is because this is where a lot of really, really rich coal beds come from. Basically, some of the environments that preserve fossils from this time turned into coal, and that's how we found them. Here in the U.S., the Carboniferous is often subdivided into the Pennsylvanian and the Mississippian, both named because of coal found in those states. During the Carboniferous, we have some other really cool animals starting to come about. One of my personal favorites from this time period is Arthropleura, which is a millipede that's about 6 feet long. We also see dragonflies getting really big in the form of Meganeura, really big bugs, really cool amphibians, all kinds of stuff through there. And then, once we get into the Carboniferous, we get into the Permian. about 299 million years ago is when the Permian starts. Now, the Permian is really, really cool because some of the more dominant animals from this time are synapsids, basal synapsids. Now, you might be wondering, what exactly is a synapsid? And if you look at every single mammal alive today, they're examples of synapsids. Synapsids are characterized basically by whether or not they have a single hole kind of behind their eye on their skull. So if you put your hand on your temple and kind of bite down, you feel a little bit of movement, that's because we have a tiny little hole right there. And at this time, synapsids were kind of in their heyday. Animals like a Dilophosaurus or Dimetrodon. We also start to see, things like archosaurs and things like that. But archosaurs really, really come into their own after the end of the Permian. So the end of the Permian marks the beginning of the Triassic, 252 million years ago. Now, it's important with the Triassic at the end of the Permian to talk about what happens in between those, and that's where we have the Permo-Triassic extinction, otherwise known as the Great Dying. This is a massive, massive extinction event that leads to somewhere up north of 90% of all species on Earth going extinct. So that's where we stop seeing Dimetrodons and things like that. Some of the synapsids obviously make it through, otherwise we wouldn't be here today. But another group of animals, about a little bit into the Triassic, about 230-ish million years ago, somewhere in there, we're not entirely sure because we keep finding newer examples, comes about, and that animal is part of the group of animals we call archosaurs. More specifically, you probably know them as dinosaurs. During the Triassic is when dinosaurs kind of start to become more and more dominant, and then moving a little bit further, 201 million years ago, during the Jurassic, is when they're kind of in their heyday. Now, from the Triassic to the Jurassic, we see some changes in some of the different types of dinosaurs we're going to see. During the Jurassic, some of the big ones that we know of here from South Dakota, Wyoming, the United States, are animals like Stegosaurus, big sauropods, the long-necked dinosaurs like Camarasaurus and Diplodocus, and then, of course, meat-eating theropods like Allosaurus. After the end of the Jurassic, we get into the Cretaceous, give or take 145 million years ago. Now, the reason the Cretaceous is interesting here is because here in South Dakota, for big parts of South Dakota, during the Cretaceous, we're actually underneath a seaway we call the Western Interior Seaway. If you look in some of the fossil-bearing formations from the Cretaceous in South Dakota, you might find animals like mosasaurs, these big marine reptiles. You might find plesiosaurs, another type of marine reptile. You might find things like Hesperornis, which is a big swimming bird from that time. You might even find animals like Archelon, which are these giant sea turtles. It's basically a sea turtle with a shell that's 12 feet across. And during the Cretaceous, while the dinosaurs are kind of like the big famous guys and the big marine reptiles are the ones we think about, it's still important to remember that mammals are still scurrying around at that time. And then at the end of the Cretaceous, we have the start of the Cenozoic with the KPG extinction, otherwise known as the Cretaceous-Paleogene extinction, otherwise known as where we see this massive meteor hit right off the coast in the Gulf of Mexico and results in the extinction of the dinosaurs and a lot of those marine reptiles. But some animals, including mammals, survive. So the Cenozoic starts about 66 million years ago, or about 197 feet on our tape measure, which goes right about here. Now, one of the things when we talk about Cenozoic paleontology is oftentimes we will divide into things like what we call epochs. So if you've ever heard of like the Miocene, the Oligocene, the Paleocene, the Pleistocene, we divide those up a little bit more just because we have more and more fossil record. Basically, the further back in geologic time you go, the more sparse your fossil record's going to be. The closer you get, the more fossils you're going to find, just because there's less time for them to get broken down and eroded and destroyed and things like that. So the beginning of the Cenozoic kind of marks the beginning of what we call the age of mammals. Cenozoic itself means recent life. And when we look at all the animals we have alive today, some of the most dominant ones we see are mammals. The next one, we're going to skip all the way to the start of what we here at the Mammoth Site get most excited about, which is the start of the Pleistocene about 2.6 million years ago. Now, just to give you an idea of how long ago that was, the Pleistocene starts right about 199 feet and about 11 inches from the atmosphere. So what that means is the Pleistocene exists within the last inch of our tape measure, and all of human existence can fit within that last inch of our tape measure. Now, when we look at all of the different things that we see, oftentimes when we look at that and we think, oh, we haven't been around all that long, that's true. But when we look at the grand scheme of all of the stuff that's existed through geologic time, it's one of the cool things is to see how we fit into that tapestry. When we look at all of the events that happened throughout geologic time, each one of those events had a ripple effect that led to humans existing and us existing the way we do today. Without the giant mammoths and animals of the Pleistocene, we wouldn't have the Mammoth Site here. We wouldn't be able to study mammoths that we have here. Without dinosaurs going extinct at the end of the Cretaceous, odds are mammals wouldn't exist in the same way that they do. Without even the great oxygenation event 2.4 billion-ish years ago, we wouldn't have the wide variety of animals we get to see alive today. So we're one part of this the geologic timescale, but we're also, what's really cool is getting to see how it all fits together. With that, I want to thank you guys for tuning in, and we'll see you next time.